In the last video, we looked at higher order partial derivatives. Now we want to think about what they mean geometrically, okay? And we are going to talk about the monkey saddle. It's kind of an interesting figure. But before we do that, I just have a question that I want you to think about. If we look at those higher order partial derivatives, and we'll just look at the second order derivatives first. So fxx, fyy, fxy, fyx. I want you to pause the video and see if you can tell me what these mean. Well, okay, hopefully you had some interesting comments or things to write down. And really, if we think back to our understanding from Calc 1 about what a second order derivative means, it has to deal with concavity, right? So really this is talking about, at least in the case of the partial derivatives that are not mixed, this is referring to the concavity in whatever direction your variable is. So concavity in x direction. Okay, and then just a reminder, we're talking about this as concavity on an interval, right? We don't talk about concavity being a single point or a function being concave up or down at a certain point. And so this would also be concavity in the y direction. Okay, the other two, these are a little bit more interesting, and we'll talk about these in our next figure. Essentially, what we have to do is we actually kind of look at it as like, oh, let's look at f sub x as we apply a derivative of y. So we talk about it kind of in that way. So really, it's the rate of change of f sub x in the y direction. Okay. All right. So, on to the illustrious monkey saddle, okay? Kind of an interesting figure. The reason it's called a monkey saddle is because if you imagine, you can put a little monkey, his head would be here, and then, okay, he's riding a saddle, and then his legs go here, and then his tail goes down there. That's why it's called a monkey, okay? But enough fun for now, because math is not fun, ever. And this is where you laugh. But anyway, so we want to look at the mixed, or the partial derivatives f sub xx, and we want to look at f sub yy here. Okay, and also I have labeled on my graph where the point A is, so that's right around here. Okay. Okay, so if I think about this, f sub xx is going to look at, again, at the concavity in the x direction, and keep in mind that x is over here. I've rotated the axes just a little bit on us, and so if I look in the x direction, I can see that there's this bending up, so I would actually say that the second derivative here, or f sub xx, is going to be greater than 0, meaning that it's concave up. Okay, now f sub yy, again, I'm looking for bending in the y direction. Again, y is kind of going in and out of the screen. And so here I can see, okay, well, it's doing this, and then this is kind of where the monkey would sit, right? And his legs would go over on both sides, and this is going to form a curve that is bending down. So this one, I think, is where the second derivative is negative. Okay? So at least graphically, you can do it looking for bending. If you're looking at f sub xx or yy, you could compute them, right? You could find, you could do f sub x is equal, and then just find it all analytically too. That works. But graphically, we want to have some sense. Okay. Now, the next, we're going to talk about another saddle, and this one's a little bit more interesting. So this is just xy, and I think we've seen this curve before, or this surface before. Okay, and if we do this analytically, because and I forgot to put a point here, so let's just, it's supposed to be like right there, so let's call that point A. Okay. And now let's just look at the partial. So fx is just y and fy is just x. And then if we do mixed partials, f sub xy, this is 1, and we actually get the same for f sub yx. Okay, and so now this is kind of interesting, because if I look at my curve, and I'm going to do this in a highlighter, let's try this. Let's do pink. Okay, if I look at, say, this first one, okay, I'm going to see that, okay, well, as I increase, oh, actually, I want to do the other one. Let's do the other one. Let's look at that one. Okay, so I'm looking at f sub y in the x direction. So I can see, okay, well, it's starting flat, flat, and it's getting steeper as I go out, right? Okay, so what I'm thinking here is, okay, I know that, well, 1 is clearly positive, right? But I'm noticing that as x increases, f sub y, which would be the rate of change of the surface in the y direction, so again, keep in mind y is right there, f of y, it's increasing, right? Okay, and so really visually, this makes a lot of sense, what we're seeing. So, and this is also because we know that the second derivative is greater than 0. Well, it's 1, right? So we're going to see some positive bending in f sub y as we increase x. Okay, so that's how we can kind of think of that second order mixed partial, is kind of chunk it in that by the first one and look at how that changes as we increase in x. If it's positive, it's going to bend more up. If it's negative, it'll bend more down. Okay, and that's just a quick video on the geometric interpretation of these partial derivatives. We'll keep talking about Clairaut, or at least a super version of it, in the next video.